Well, thank you all for joining us. As she said, my name is Michael Jennings. I am a scientist at Los Alamos National Laboratory in New Mexico. Before that, I spent almost 10 years as a lead sysadmin in the HPC services group at Lawrence Berkeley National Laboratory. Serving the scientists there, I also did the architecture for Werewolf 3, wrote LBNL node health check, along with a few other projects. So I've been doing HPC for about 11 years now. For those who aren't familiar, Los Alamos National Lab is part of what we call the Tri-Labs, a group of 3 national laboratories, ourselves, Lawrence, Livermore, and Sandia. Together we are responsible for ensuring the safety, security, and effectiveness of the United States nuclear stockpile. Back in 1992, the powers that be decided that maybe blowing up nuclear weapons wasn't such a good idea. And so we, ever since then, have been required to limit ourselves only to what we can simulate on computers. The upside of this is that we then need to make sure that we have very large, very fast computers with which to do these simulations. Even before then, though, Los Alamos has had a long and storied history with high-performance computing, dating all the way back to the 50s. Among other things, we had the very first transistor-based supercomputer designed and built with IBM, something called Stretch. We had the very first #1 on the top 500. And of course, I think we've talked earlier this week about Roadrunner, which was the first petaflop supercomputer. It was also the first hybrid supercomputer, combining traditional CPUs with the PlayStation cell processors. And if you've heard of data warp or the term burst buffer, that was a technology that was designed by a gentleman named Gary Grider. He leads our high-performance computing division now. We do a lot of classified research, but we also do a fair amount of open science, everything from cancer research to environmental sciences. We serve well over 2,000 users across 100 different projects between our classified and our unclassified systems. So we've been at this a long time, but recently things have been starting to change. Traditionally, HPC has led the way in scalable computing technology. But with the advent of the Googles and the Facebooks and the Amazons of the world, suddenly we're not the extreme scale anymore. Hyperscale is leading the way, and we're finding ourselves having to buy whatever they are being sold. It has also meant that the students who are coming out of college are in a little bit different world than what we remember. And as a result of this, we are facing some unique problems that we really hadn't faced before. Traditional HPC systems are really, really good at one specific thing, and that is running MPI code at scale, tightly coupled, massively parallel code at scale. And we've built our systems over the years to do exactly that. And they're very good at it. But if you want them to do something else, that's where you start running into issues. And as I mentioned, those of us who've been around a while and are set in our ways learned in a very different world from what the students have been learning coming out of college and going into industry. I cut my teeth on all the various commercial Unixes, as well as something called Slackware, for those of you who remember Linux in the 90s. And the original Red Hat Linux, not Enterprise, the original Red Hat Linux. Nowadays, a lot of the mind share is in the world of Ubuntu. Partly because it's a very clean and polished and easy to use operating system, and partly because every piece of software that's ever written can be apt-get installed on an Ubuntu system. So it makes it really, really easy for somebody who wants to spend their time developing to get right to it and not have to worry about going through dependency hell in RPM land, trying to figure out how to get all of these Python modules built into RPMs, and so forth. The other thing we run into, if someone asks us for something that our system doesn't already do we say yes or do we say no? We actually do get people who want us to install the very latest glibc that's not even been released yet. It's a branch in Git. They say, why can't you install that? I don't understand. It works perfectly fine on my workstation. Yeah, okay. And they don't understand why we can't give them root access. I mean, shouldn't everybody have root? I mean, it's a free country, right? So these are problems that we have to figure out a way to solve because they're not going away. They're actually getting worse. What they're really asking us for is what we like to call UDSS, or user-defined software stacks. The guys at NERSC call it UDI, user-defined images. Some people say bring your own environment. Whatever the terminology is, it's really talking about the same thing, allowing users to specify the entire software stack that they want to be running on. And traditionally, in the Unix world, when somebody has needed to bring all of their dependencies along with them, the solution has been what? Static binary. Static binaries, all of your dependencies come along with you. Works great if you've got a C or C++ program. Python script, not so much. So we need options. We need solutions to this problem. And the most obvious solution is tell the user, go off and compile it yourself. Not my problem, your problem. Go fix it. In theory, that works just fine. Any piece of software, ultimately, as long as you have the source code, you can compile it, you can install it yourself. And if you've got instructions or, this little thing called Google, chances are you can be successful at that. The problem with this approach is it very quickly fails to scale. One software package is easy to build and maintain yourself. But then you've got supporting libraries, you've got Python modules, and every one of these things you could potentially have to build with any number of compilers, any number of MPI stacks, and so forth. So the problem gets exponential very, very quickly. It's the 21st century. We've been attacking this problem for an awfully long time, and surely we've been able to come up with something better by now than the same kind of configure, make, install I was doing in college in the mid-90s. And a term you're going to hear a lot, at least from me, if you haven't already heard it this week, is reproducibility. Just because you did it once does not necessarily mean you're going to be able to do it again. So is this the right solution to our problem? Well, no, probably not. In the world of HPC, the traditional answer to this has been use an environment manager. Think environment modules. If you're anything like ourselves, we have an entire group of technologists whose job it is to build every piece of supporting software that our users need with every combination of compiler, MPI library, linear algebra library, supporting library, and so forth. And so you get these directory paths and binary names that have 15 different software packages in them. And it gets absolutely ridiculous. But it's the way we've been doing things for a long time, and theoretically it's workable. If you have to go this route, there have been some actually pretty good attempts to solve this problem in the traditional way. Things like Lmod and Spack coming out of Livermore. There's a project called EasyBuild that is from the University of Ghent here in Europe. They actually do a lot to solve this problem in a relatively smart way. Given the constraints, it works pretty well. But again, we'd like to find a better way, a better solution to address this problem that doesn't require all of this building of all of these combinations of software over and over and over again. I should also mention NixOS. NixOS is a distribution engine where you create a configuration file and you tell it what you want it to install on your system, and it takes this and, based on your prescription, installs and configures packages into a distribution on your system. You can manage your entire distro with this. You can also tell it to install into your home directory and maintain your own set of software locally. We've had users do this and have had pretty good success. So that's an option as well that a lot of people in the HPC admin world don't necessarily know about. Option number 3 is virtualization. If you've been an admin in HPC at all in the past 5 years, at least a dozen of your users have come up to you at one point in time and said, why can't you just make this the cloud? Why can't you just install OpenStack on your HPC cluster and let me run in a VM? That solves all my problems. Well, yeah, it solves your problems. It creates about 1 billion new ones for me, and you're not going to get the results that you think you will. Virtualization has come a long way in the past decade or so, but a lot of the complaints that we've had about virtualization and the ramifications of trying to run HPC on virtualized hardware still remain to this day. There's a specific performance hit that you take every time you try to do something in software rather than hardware. And for all of the things that have to be done in emulation, there's an additional performance hit for each and every one. It can also be extremely challenging to get access to the high-performance hardware that has made HPC over the years. Things like InfiniBand and OmniPath, GPUs. Those don't always get along with virtualization very well. Now, there's a lot of work in that direction to fix that, but for right now, it's still an issue. Some use cases will perform well as things are today, but it's not a general purpose solution for HPC. And unlike other solutions that we've talked about, when you're dealing with a virtual machine, you have a complete entire operating system that you have to boot up from scratch. It's got its own identity, it's got its own host name and IP address and all these things that have to be maintained. You have to configure services or turn services off and so forth. So it's not just as simple as running your application inside of a VM. You actually have to boot the thing and get it set up correctly. So should HPC become the cloud? Maybe. If we can address some of the challenges that we have today, I think there's going to be a convergence down the road where HPC and the cloud aren't going to look as different as they do today. But in the world we're living in right now, no. You're not going to get the speed, the performance, and the results that you need. So option number 4 is something that you've already heard quite a bit about this week, but hopefully I'll be able to provide some new information. Containers. Containers, in our opinion, strikes the correct balance between the needs of performance, access to hardware, etc., and allowing users to specify the environment that they want their applications to run in. Obviously, there are some implications for security, and we need to understand those. And when it comes to containers, security is an area where there's been a lot of misinformation, a lot of misunderstandings, a lot of confusion. So I want to try and clarify some of that. Containers are extremely simple and easy to use once you get used to them, and assuming you choose the right option. And they do allow you to define the environment that your application is going to exist in. And if you do it right, you can do it in a way that's prescriptive and reproducible. You have multiple options for identifying to others how to create the exact same environment for themselves and potentially reproduce not only that environment, but your results as well. There are some downsides. You either need to have a recent version of the operating system, or you need to accept elevated privileges to run containers. And as I mentioned, container expertise in HPC is hard to come by these days. And there's a lot of bad information that's been going around as a result of that. Even some publications have come out with factually inaccurate and misleading information. Sorry. It's okay. The biggest thing, and where we need to start, is what the hell is a container? You ask 20 different people, whether it's an HPC or the cloud, it doesn't matter. You ask 20 different people what the definition of a container is, you're going to get 20 different answers, and no 2 of them will be the same. And that doesn't mean they're necessarily wrong. Containers have meant a lot of different things over the years. This is not a new feature. You've got Solaris zones, you've got FreeBSD jails, you've got OpenVZ, you've got Linux vServer. The problems associated with chroot and the fact that POSIX mandates a way to break out of a chroot, but we really, really want to use it for security reasons, that mess has been trying to get fixed for longer than I've been alive. And it's not going to go away overnight, but we're finally getting closer to the right answer. So what is a container? Well, this is our take on containers. Again, you'll hear other definitions, but this is the one that we're going by. Containers leverage one or more of a kernel feature called namespaces. And I'll go into more detail about that here in a little bit. Namespaces provide a customized or isolated view of resources on the system. And we use containers to encapsulate and envelop processes and applications so that it's impossible for them to escape and see the true view. Now, I say impossible because, you know, nothing's ever really impossible when it comes to computers. But if everything is done correctly, and barring any bugs in the kernel, it should be impossible to break out of the container that we create. And so we can control exactly what the application sees when it looks out onto the system. Containers also facilitate security of our applications using capability constraints. That means controlling what they're allowed to do and what they're not allowed to do. Integrity assurance, things like non-repeatable signatures, content addressable storage, hashes for content, so we know that what was in there when it was created is the same as what it's in there now. And if it changes, we can't get to it. And content validation using industry standard formats and workflows. That means we're not reinventing the wheel for no reason. So that's simply how we define containers. Namespaces, okay, there's another term we need to talk about. What are namespaces? Namespaces started out with just changing the view of mounted file systems. In the very beginning, nobody thought anyone would want to do anything with namespaces other than change mount points. And so the flag for creating a mount space was literally new namespace. Everything else has been kind of an afterthought that came after that. So namespaces, there's 6 of them in the 3.10.4.4 kernels. The newer kernels starting at 4.6 and beyond have 7 namespaces that are what we call privileged. Privileged namespaces, you have to have a particular capability in order to create them. If you're familiar with Linux kernel capabilities, it's kind of a way of divvying up the powers that root has traditionally had so that you can dole them out on an individual basis. For example, ping. Ping used to be set UID root because you have to open a raw socket to ping something. If you look at your RHEL 7 box, it's no longer set UID root. Why? Because there's a flag on that binary that gives it capnet admin and capnet raw, allowing it to create raw sockets. So now we can give ping the capabilities, no pun intended, that it needs without having to have it set UID root. Now that's great in theory, but with all categorizations, there has to be some dumping ground for everything that we can't figure out a better bucket for. And the dumping ground in Linux is capsysadmin. So if there isn't a dedicated capability for it, chances are capsysadmin is the capability. And as with many other things, capsysadmin is what you need to create any of these namespaces. The most obvious one, again, is mount. The mount namespace gives you a customized view of the file systems on the machine. So if you create a new mount namespace, you can potentially unmount file systems and mount new file systems and bind mount here, there, and everywhere and have a completely different view of / and everything under it from the rest of the machine. This is great for doing chroot the right way. PID namespace, or process ID namespace. When you create a new PID namespace, the first process in it becomes process ID 1. And that's all it can see. It cannot see any other processes on the system. Now, if you're familiar with what PID 1 is on a Unix system, init, or systemd, but init, when something dies, it gets reparented to process ID 1. So whatever that process is, it is the init in the namespace. And all of the associated caveats and responsibilities of waiting on processes, it has to be able to handle those things. And any children of that process get their own PID inside that namespace, starting with 2 and 3 and 4 and so on, and again can only see those processes. Now everything else on the system that exists outside that PID namespace can still see those processes. It just sees them with a different process ID. UTS, Unix Time Sharing System, really bad name, but that's the name of the data structure in the kernel that holds the host name and the domain name. So a UTS namespace, all it can do is give you a custom host name, custom domain name. Network namespace. Network namespace gives you your own private, essentially TCP/IP stack. So you get your own IP tables rules, you get your own interfaces, you get your own routes, all of that type of stuff. You get your own customized network playground. The downside is the only interface you get is loopback. Everything else you have to do yourself. IPC, POSIX message queues, semaphores, shared memory, System 5 IPC, all of that stuff goes in that namespace. As you can imagine, creating a new IPC namespace when you're doing like MPI jobs and stuff, not a good idea. So we generally steer clear of that one. And the brand new namespace in the more recent kernels is the cgroup namespace. We'll talk about cgroups in a little bit. Cgroup namespace gives you your own custom view of the cgroup hierarchy. Now there's one namespace that I haven't talked about yet, and that's the special one. And it's what we call an unprivileged namespace because you don't have to have capsysadmin to create it. Anybody on the system, assuming your system is properly configured, can create a user namespace. And once you do that, you can create any of the other namespaces. Because when you create a user namespace, while you have no capabilities in the parent namespace, you have all the capabilities in the user namespace. So an unprivileged user can create this user namespace and become root inside that namespace. And then they can do all of the other fun stuff, but only inside that namespace. Christian, I was waiting for you.
No, I haven't tried it out myself, and it's not really usable yet, but have you tried out the RDMA? There's an RDMA namespace.
Really? Which kernel did that show up in?
1 or 2. It's 2 years old.
No, I haven't. And I should mention that there have been a few namespaces that people think exist. I'm not saying this is one of them. People have talked about a dev PTS namespace. There's no such thing. But they are coming up with new namespaces on an ongoing basis. RDMA, I'll have to check that one out. That would be handy. Yeah. Yeah, definitely should play with that. So namespaces are actually a really, really simple and straightforward thing. There's only 3 system calls that define the entire API for namespaces. Just 3. There's unshare, which takes the existing process and puts it into one or more new namespaces. So you're unsharing your namespace with your parent and going off on your own, kind of like leaving for college. There's the clone. If you've ever S-traced a process, you've probably seen clone where you thought you would see fork. Clone is the Linux system call for creating a new process. Linux threads are also done with clone. So clone can be used to create new namespaces as well, specifically new processes inside new namespaces. So when you fork off a process using clone, you can tell it, I want that process to be in this, that, and the other new namespace. And then the third system call is setInS. setInS takes an existing namespace that already is out there on the system and puts your process in it. That's it. There's no other system calls. That's all there is to it. Really, really simple concept. And a lot of people freak out about containers and how complicated they are. They're really not that complicated. This is all there is to it. If you're not familiar with namespaces, but you would really like to learn more, this article is awesome. It's actually a series of articles on Linux Weekly News that goes through step by step everything you ever wanted to know about namespaces and then some. And there's code in there you can actually kind of play along, write your own little miniature container engine. Really good stuff. Highly recommended. So it's not just namespaces. That's where you start. Then there are some other kernel resources that we make use of as well. C groups are the big one. C groups or control groups allow us to do what HPC admins have been struggling to do for years. Put strict limits on memory, CPU consumption, network bandwidth consumption, etc. on processes and have them enforced by somebody other than Torque sitting there going, let's see, how much memory? Okay, how much memory? How much memory? Oh, too much memory, kill you. That kind of thing has been going on for way too long. Now we have a way that's enforced by the kernel to set limits on processes. So C groups allow us to constrain resource utilization by processes. And we can create C groups and manage not only what the resource constraints are, but how things are handled if they get violated. For example, you can essentially create your own killer. Or you can get notified if there's an event and react to out-of-memory conditions in your own way. So there's lots of cool stuff you can do with C groups. Seccomp BPF. Seccomp, as we learned earlier in the week, is a way of limiting the system calls that processes have access to. They really struggled for a long time to get this right in the kernel, because trying to control what processes had access to had huge performance implications until they came up with the idea to use the Berkeley packet filter JIT compiler and bytecode language that was already in the kernel. Instead of using it for packet filtering, use it for system call filtering. It's extremely fast. And this was such a success that now they're doing it for performance monitoring. So Seccomp BPF allows you to specify which system calls are and are not allowed from a process. SSH uses this. to lock down their stuff and make sure that if somebody tries to exploit it and do something naughty like open an unexpected socket, whatever, that the process gets killed by the kernel. PRCUDL is a general privilege control system call in the kernel, but there's a particular flag that you can set that every container engine that I'm aware of uses and should use to make sure that escalation within a container is no longer possible once the application gets launched. So this basically says the privileges I have now are the most privileges I can ever have again. Once this flag is set, it can never be unset, and it's enforced at the kernel level. So no more setUID processes, etc. SE Linux and AppArmor, there's a bit of a religious war between those two. SE Linux is a multi-level security mandatory access control system that uses labels to define who can do what on a Linux system. AppArmor is a profile-based mandatory access control system. AppArmor tends to be a lot easier to set up and use, but isn't nearly as powerful. So there's a bit of a conflict between the two as to which is better and which is more secure, because things that are overly complicated often aren't secure. I'm not going to get into that religious war, but I will say that at least if you're using containers for system type things, you should have at least one of those going, or your containers probably aren't secure. So the container landscape has been growing and changing and developing extremely rapidly. It's very difficult to keep up with, even for people like Christian who are in the thick of it every day. Certainly for us in HPC, it can be tough to keep up with all of the different things that are going on, the different efforts. There's a lot of people working on filling in the gaps that we have in containers. And so keeping up is hard to do. We divide the container landscape into basically two general categories, one being full-featured container systems. These are systems that try to solve all the things. They want you to be able to do builds, distribute containers, secure containers, execute containers, all of the different tasks associated with containers they try to solve. Docker obviously is the de facto standard, has been for some time. There are alternatives. I used to have Rocket here, but Rocket seems to be largely abandoned, particularly now that Red Hat bought CoreOS. In its place, though, is something called CRIO. CRIO came out of a combination of Project Atomic and OpenShift at Red Hat. They're doing a lot of work to address what they feel are challenges and shortcomings with Docker. So they've got an entire ecosystem built up around containers that do things differently. There's also LXC and LXD. They kind of started the whole show. Docker was originally based off of LXC. Of course, they've gone in different directions now at this point. LXD seems to be going more in the virtualization, cloud management, replacement direction. So like LXD offers live migration of containers and neat stuff like that. Whereas Docker went in the direction of application containers, specifically tying applications to the environments that they are to run in. So most modern container systems are compliant with the Open Container Initiative, and they should be. That's the industry standard that says how all of the things are supposed to work and supposed to work together. It started essentially with Docker contributing their code to the community for their runtime and their container management system, runc and containerd. And those kind of kick-started the process. The work of CoreOS on Rocket was incorporated in for content addressable storage and non-repudiation. They just recently announced that they're going to start standardizing distribution, meaning how registries work and how you communicate back and forth with a registry to pull and push image layers. Now, the one thing OCI doesn't do is define a standard or a spec for builds. The de facto standard in the industry today is Docker files. Pretty much everybody who's doing container builds is either Docker or they support Docker files. The one exception was Rocket. They had something called EasyBuild, which was more of a traditional shell-based make integration type system. And then the new kid on the block is something called Builda. It's supposed to make fun of Dan Walsh's Boston accent, apparently, hence the name. Builda is their solution for building containers. It does support Docker files. It also has its own unique syntax for builds. On the other side, we have the lightweight container solutions. Generally, those are only trying to be a runtime. They either rely on the overall Docker OCI ecosystem to do everything else, which means they don't have to resolve a lot of the problems like security. Runc, I list runc because there are a lot of people who are doing things with runc by itself outside of Docker. Rootless runc, if you rootless containers, container.rs, they're doing a lot of work with rootless runc so that you can do unprivileged containers with the standard OCI runtime. Ccon is an OCI project that is a runtime implementation in straight up C. Nice, clean, small, lightweight. NSJail is a Google project. Something a lot of people don't realize, unshare, I talked about the unshare system call. There's also an unshare command. If you have util Linux installed on your system, any recent version, you're going to have an unshare command that can create all of those different namespaces that I talked about earlier. I've actually handwritten in about 2 hours a customized container solution to control and restrain a particular daemon that we felt was possibly a security issue. So you can do a lot with containers with nothing but a bash script. There is something called systemd nspawn. Systemd has everything, so of course it's going to have its own container engine. The difference with systemd nspawn that you have to keep in mind is it's systemd. So it's going to expect a complete system image, not just the application, but an entire system. So it expects to be able to boot your container, not just launch an application. If you've heard containers called lightweight virtualization, they're really not, but this sort of thing gets you closer by booting a container. And of course, Charliecloud. So let's talk about security for just a minute. Container security is a really hot topic. Cybersecurity has always been what a lot of people refer to as an onion. You've got layer upon layer upon layer of protection, defense in depth. If they break through one layer, they hit another layer. It's not just a simple yes or no binary question. You may have heard, with respect to some other HPC-focused container solution, the phrase, you have the same UID inside the container that you have outside the container, and therefore it's secure. Unfortunately, that's just not true. If I told you that you should go and find binsh and binbash on your system and make them set UID root, and I told you it was perfectly safe because when you run it, your UID will be the same, you would think I was completely off my rocker, and rightly so. Security is not just a question of whether or not you appear to have the correct identity. Security is a question of attack surface. It's a question of privilege separation, privilege boundary, and who is managing what information that entity has, and how it uses that information to keep you safe. Container security relies on a lot of different parts and pieces all working together to keep you safe. If you think about transport, when you take a container from Docker Hub and download it to your system, what keeps that secure? What keeps that safe? Non-repudiable signatures on content, layer hashes, and content addressable storage. If anything in that layer changes, its address changes, and therefore you can no longer get to it. So you know that when it gets to you and gets on your system and you can access it, that it has the same content it had when it was built. When you run it, container security relies on all of those things that I mentioned earlier, the privilege system calls, the seccomp stuff, the MLS system that you use, or the Mac system that you use, SE Linux, AppArmor, all of those different things. But ultimately it boils down to your kernel. Container security relies at minimum on the security of your kernel. If your kernel has a bug, all bets are off. The question is, how much, in addition to your kernel, are you relying on for container security? And how much additional attack surface within the kernel is your container solution exposing, and how is that handled? No matter what container solution you choose, we are fundamentally offering traditionally privileged operations and powers, capabilities to unprivileged users for the first time. There's a reason root requires root privilege. So exposing these powers to unprivileged users comes with a risk. It creates a new security boundary. So each site, each admin has to make a decision. Where do you want that security boundary to live? And how do you want it to be managed? Do you want to rely on a solution that has known security issues and doesn't maintain that security boundary? Do you want to pick something that uses a well-understood but problematic security boundary and has to be run setuid root? Or do you want to pick a solution that makes sure that the kernel itself, the security boundary that you've already accepted in order to run Linux, has all the information necessary to determine who has what privilege and make the appropriate decision. That's what user namespaces gives you. The kernel knows which processes have what level of privilege in what context. With setUID operation, you're basically hiding from the kernel the fact that this process or this user is unprivileged. As far as the kernel knows, it's UID 0, it's root. So the kernel loses essential information that could help it make better decisions to protect your system. Now, the vast majority of the development in this space that's going on right now is associated with user namespaces. The Googles and Facebooks and Amazons of the world are focused on this area. And new parts of the kernel that traditionally were never exposed to a normal user are now. But because so many eyes are focused in this direction, problems that are coming up are getting fixed pretty quickly. For those cases where user namespaces and things like that are involved. So why should you use Charliecloud? How am I doing on time? Yikes, okay. So why isn't Docker the right solution for HPC? You've probably heard a lot of answers to that, many of them wrong. It has nothing to do with the Docker daemon being root. I think it was Christian who pointed out that slurmd runs as root and spawns jobs on your compute nodes. So saying that it's a problem with having a root daemon in charge of stuff, ridiculous. The problems with Docker, most fundamentally, you start with performance. OverlayFS, we've been talking about OverlayFS. OverlayFS was written to be simple to implement, simple to understand. It was not written to be performant. Each layer gets new files laid on top of the previous layer. What happens if you want to remove a file? You can't go down to the previous layer and get rid of it. So there's actually what's called a whiteout file. .wh.filename, literally that gets put into the higher layer to remove stuff. Which works okay for normal files, but when you think about things like your RPM database, which is a big binary file and a whole bunch of indexes, it causes all sorts of fun behavior. There's actually a Yum plugin that is required if you want to do OverlayFS and Yum and have them get along well. And every layer that you go through is a performance penalty. So OverlayFS, easy to implement, easy to understand, performs like sewage. That's reason number one why Docker isn't currently the right answer for HPC. Another one is the associativity. There isn't really a good way right now for a workload manager to associate the container process that was spawned by the Docker daemon with the CLI that launched it. So that associativity is a problem that needs to be solved. And if you know what command line parameters to supply to Docker and you have access to the Docker CLI or the Docker socket, you can get root on a host. Not because there's anything wrong with Docker, but because the default authorization mechanism is let the user do everything. And pluggable authorization modules are an enterprise edition feature. But again, this is a solvable problem. And not just by paying Christian a lot of money and licensing enterprise edition, though we'd all love to do that. Absolutely. But this is a solvable problem. On the flip side, NERSC's shifter is an extremely well-engineered piece of software. Doug made explicit technical choices for each and everything that he did. The user experience with shifter is absolutely incredible. Most of the users that we deal with, if they want containers, they're coming to us and saying, I have this Docker container, I want to run my job in it. Bottom line, that's it. And shifter, from the user's perspective, is essentially that. You tell it to download an image from Docker Hub, you tell it that's the image you want your job to run in, you're done. The side effect of that, though, is that the admin, in order to set that up and make it work, has a buttload of work that they have to do up front. So there's an image gateway to set up, and there's parallel storage that they have to set up and make sure all of those things work. But once they do that, scalable job launch works great, and the user doesn't have to worry about it. So there's definitely a trade-off there. I mentioned several times how simple and straightforward the container API is in Linux kernel. And a simple API ought to result, in most cases, in simple code. Charliecloud is less than 1,000 lines. Some of it's C, some of it's Bash, but less than 1,000 lines of code. And you can see what the other projects weigh in at. But most importantly, in my mind, with Charliecloud and similar runtimes, the boundary is the kernel, period, end of story. Any other solution that relies on set UID, you're going to have additional attack surface, you're going to have an additional security boundary that program then becomes responsible for maintaining. And that program is then potentially exploitable. With Charliecloud, with user namespaces, the entire security boundary is 100% the kernel. You've already accepted that as a security boundary. You're running the Linux kernel. And so you're not accepting any additional security boundary. You are accepting an additional feature, an additional capability, and the risk that may be associated with that. There's some other projects down there that I noted that are also worth watching. Rootless Run C is #1 on my list with a bullet. Hopefully, if things go according to plan, in the next year or two, we'll see some interesting developments in that arena, and that's all I'll say there. CRIO also looks extremely promising. They're doing a lot of stuff with specifically trying to get rid of the Docker daemon, but have everything else work essentially the same way. So definitely we're paying attention to that.
Questions at the end or comments, questions?
Yeah, just give me a, let me get through this real quick. I'm almost done, and then I'll come back to you. So this is a really quick walkthrough of Charliecloud. You either build your container with Docker, or there's a Charliecloud chbuild wrapper, but you can build with Docker directly either way. Or you do a Docker pull and download it from Docker Hub or whatever your registry server is. You do ch docker to tar, and then ch tar to dir, and you get a directory. That directory is essentially the same directory that the OCI runtimes rely on being there. So it's essentially the same model. And the top box is the part that requires privilege. So you can either do that on your workstation with Docker, or if you want to use a different tool to build, you can do it in a user namespace on your HPC resource. Either way. Then the tar2dir and the chrun, those are unprivileged operations, and typically If you're talking about a parallel job, both of those are going to be in your job script. SBatch, PBS, whichever you're doing for job launch, that's going to be in your job script to do the distributed unarchive and then execute. Tomorrow, for anybody who's interested, we're going to have an extended Q&A session with Christian, myself, and oh gosh, my mind's blanking. Abhinav, thank you. Abhinav, Christian, myself, we're going to be taking questions, answering questions. We're also going to be doing some live demos of the various container solutions. So that's tomorrow afternoon, 1:25 to 5:30, I think. Obviously, yeah, all afternoon after lunch. Obviously, you don't have to stay for the whole time. Come and go. Ask questions. We'll have various demos. I've got a TensorFlow one here on my laptop that runs through a Jupyter notebook under Charliecloud. I've got a Vagrant file for people who want to try out Charliecloud in a VM. So performance is always the big question. What's the performance penalty? It's essentially in the noise in our tests. And as you would expect, it's all namespaces. It's all inside the kernel. So there should not be any sort of performance penalty that's measurable. Oh, I should mention, those were 32 node MPI jobs, average of 3 runs. If you want to learn more, obviously I'm going to be here the rest of the week, so you're welcome to ask me. We've got the session tomorrow that I'll be around for to ask and answer questions. There is a supercomputing 2017 paper that was done. There's also an article in Login Magazine about Charliecloud. So those are really good resources. We've got the repository on GitHub. It's really easy, HPC/Charliecloud. And there's the read the docs format, Sphinx format documentation on github.io. We've got mailing lists. We decided to use groups.io just for the halibut because we hadn't tried it yet and wanted to. And of course, you can contact Reed, who's the lead author of Charliecloud, or Tim Randalls, who is a container and OpenStack expert who works with us, or myself. So I'm right up against time, I think, but if there's 1 or 2 quick questions, I'm happy to take them. And I know Christian has at least something to say, so I'll go to him.
Can you go back to slide 15, please? We talked extensively anyhow, but I think one thing I would like to mention is that the performance of the overlay file system should not be really of interest here, right? Because you're not putting your data in the overlay file system. You bind on something from the host, right? Or I'm quite sure I disagree.
Well, that's a fair point, except generally the power of Docker is, and containers in general, are their composability. And the ideal design pattern for working with app containers is to associate them with data containers and data volumes that would have that same flexibility to move around. We would like to be able to have portable data volume containers that potentially are backed by the shared storage but aren't directly running off of the shared storage, and use a container for that. But then we get into the overlay FS and the performance hit.
Why not using a volume driver? Like, why not using volume instead? Either a bind mount or some mount from NFS or whatever?
Understood. Keep in mind that when we first started, there weren't nearly as many storage drivers for Docker as currently exist, and the ones that did exist that weren't the default were somewhat problematic. I'm sure you've heard about the issues with the LVM thin provisioning stuff in the early days. That type of thing is what we were faced with. Obviously, you know, things have changed quite a bit since then, and we're constantly reevaluating what, as you know, I mean, we've talked about this, what the right answer is. So I'm confident that within the next year or two, the answer is going to be very different from what it is now. But those are the types of problems that when we first started looking at how do we deploy Docker on our HPC resource, the storage, the data volume situation was a huge issue. But you're right, it's less so now. Absolutely. One more quick question.
Sorry, it was not so clear for me. How do you access the host GPU and API? How do you do that you access the GPU with the host level? Do you do the same as Shifter, that you rely on the API, or how do you do that?
So it depends. The beauty of user namespaces is that even though you appear to be root inside the namespace, you are literally yourself outside the namespace, even at the kernel level. So the device drivers and everything, they will see you as you, not as root. So the access pattern should be the same. It really boils down to the software. And so you have to make sure that the correct software that's compatible with your GPU or whatever device, whether it's your InfiniBand or FPGA, whatever it happens to be, the software that's inside your container needs to be compatible with the hardware that's outside your container. But from a privilege perspective, it just works.
So just to follow up on that, then that means that when you have the Charliecloud
Or potentially build them, or it may be part of the container. Like you can download the TensorFlow container from.
user and machine specific or deployment specific.
One of the biggest pluses and minuses of Charliecloud is that the admin has to do nothing whatsoever. Users themselves can install and run and use Charliecloud with no admin intervention. But that means that the onus is on the user to do a lot more of the legwork. All right, if there are any more questions or if you want to argue with me some more, that's great. I love a good debate. Tomorrow, 1:25 in room C.